Hello, this is the third part of the chapter 6.1, and we will talk about orthogonal complements. And generally, the idea of the orthogonal complements is help us to expand our ideas of subspaces and multidimensional spaces. For example, let's take subspace W, which consists of multiple vectors. For example, here we're using our, because it's easier to plot, our subspace W is actually a plane in a three-dimensional place, Rn. We can then choose the line L, which is perpendicular or orthogonal to our subspace W. So now every single vector Z which lies in this line will be also orthogonal, guaranteed to be orthogonal to our subspace W. And actually, if we look at the, every single line which cross our plane, for example, that's not the only line which can be perpendicular to the plane W. We can choose plenty of lines like this. And this combination of line L, all of which will consist of the vectors which perpendicular or orthogonal to our space W, we will call this set of lines is an orthogonal complement. So anything which consists of the vector which is orthogonal to our subspace W. And again, here we're talking about lines and planes, but of course we are dealing with the matrices, which has a huge dimensions. So we will just rely on ideas of orthogonality. But in general, we say that the set of all vectors Z, which are orthogonal to given subspace W, is called orthogonal complement. And it denotes like with the same letter is our original subspace W, but it has like this upper index, kind of like a flip T, which denotes the orthogonality or complementarity, orthogonal complementarity. Okay, so there are several important properties of our orthogonal complements. For example, a vector X in orthogonal complement of our subspace W, it belongs there if and only if X is orthogonal to every single vector that spans our subspace W. Another important property is that our orthogonal complement is always as actually a subspace of Rn. So basically, we can always split our Rn into the subspace W and its orthogonal. And this is very important property which we will use extensively. Divide subspace into orthogonal components. But one of the important outcomes of these findings is that we finally can take a new look at our row space, column space, and null space of the matrix, because our null space of our matrix is happen to be the orthogonal complements of our row space of the same matrix. Also, the column space, the orthogonal complements of the column space of the given matrix will be equal the null space of transposed matrix. And there is a proof of these properties in the text, and I strongly recommend you to go through the whole proof and then go to the end of the chapter and practice the orthogonal complementarity properties, and maybe try to apply to the row space, null space, and column space. So hopefully it will help you to understand these ideas more deeply.